Welcome to today's paper reading. Today's paper is titled, Learning to Learn at Test Time RNNs with Expressive Hidden States. This paper was published on the AR14 preprint by Sun and colleagues from Stanford University, UC San Diego, UC Berkeley, and Meta AI. The abstract highlights the challenges with self-attention mechanisms, which, while effective in long contexts, suffer from quadratic complexity. In contrast, existing RNN layers have linear complexity but are limited in their performance due to the expressive power of their hidden states. To address these issues, the authors propose a new class of sequence modeling layers with linear complexity and an expressive hidden state. The key innovation is to treat the hidden state as a machine learning model itself, with the update rule being a step of self-supervised learning. This approach, termed test time training, TTT, layers, includes two instantiations, TTT linear and TTT MLP. These layers are evaluated across a range of parameters from 125 million to 1.3 billion, demonstrating their effectiveness in comparison to strong baselines like the transformer and Mamba. Notably, both TTT linear and TTT MLP show the ability to reduce perplexity by conditioning on more tokens, a capability that Mamba lacks beyond 16K context. Preliminary optimizations indicate that TTT linear is faster than the transformer at 8K context and matches Mamba in terms of wall clock time. While TTT MLP faces challenges with memory I/O, it shows significant potential in long contexts, suggesting a promising direction for future research. Figure 1 illustrates the concept of test time training, TTT, layers and sequence modeling. The key idea is to treat the hidden state as a model F with weights W, and the update rule as a gradient step on the self-supervised loss. This means that updating the hidden state during a test sequence is equivalent to training the model F at test time. This process, known as test time training, TTT, is integrated into our TTT layers, providing a novel approach to sequence modeling with linear complexity and expressive hidden states. Figure 2 compares the performance of TTT linear and Mamba in terms of perplexity and floating point operations, flops. On the left, it shows that TTT linear achieves better perplexity than Mamba at 760 m and 1.3 b parameters while using fewer flops. This indicates that TTT linear is more efficient in terms of computational cost without sacrificing performance. On the right, the graph demonstrates the ability of models to reduce perplexity as they condition on more tokens. Transformer and TTT linear continue to improve, whereas Mamba's performance stagnates after 16K tokens, suggesting that TTT linear is better at utilizing long context information. All methods have matched training flops as Mamba 1.4b, ensuring a fair comparison. Figure 3 illustrates the forward time per token, or latency, for a batch size of 16 as the context length varies across different models. All models examined are of size 1.3 billion parameters, except for Mamba, which is 1.4 billion. The graph shows that the forward time per token increases linearly for the transformer model as the context length grows. In contrast, the latency remains relatively constant for the other two methods, TTT linear and Mamba. Notably, TTT linear demonstrates faster performance than the transformer at 8K context and achieves comparable latency to Mamba. This data is detailed further in subsection 3.3. The introduction of this paper revisits the scaling capabilities of RNNs, particularly LSTMs, in comparison to transformers. It highlights that while Mamba, a modern RNN, shows scaling similar to a strong transformer, it still faces issues with long context sequences, as evidenced by a perplexity plateau at 16K tokens. This paper introduces test time training, TTT, layers, a novel approach where the hidden state of the model is updated through self-supervised learning. Two instantiations of TTT layers are proposed, TTT linear and TTT MLP. Additionally, the paper discusses practical innovations to enhance the efficiency of TTT layers, including the use of mini-batches and a dual form for operations, which significantly improve training speed on modern hardware. These innovations make TTT linear a practical component for large language models, LLMs. The method section introduces sequence modeling layers, which compress historic context into a hidden state. This compression is efficient for token mapping but limits performance in long contexts. The test time training (TTT) layer is proposed to address this by using self-supervised learning to compress context into a hidden state through gradient descent updates. The implementation details include using linear and MLP models, learning initial weights, and employing an adaptive learning rate for flexibility. Figure 4 illustrates the concept of a generic sequence modeling layer, showing how the hidden state transitions according to an update rule. It highlights that all sequence modeling layers can be seen as different implementations of three core components: the initial state, update rule, and output rule. The bottom part of the figure provides examples of sequence modeling layers, including naive RNN, self-attention, and naive TTT, each demonstrating how these components are instantiated. Figure 5 illustrates the self-supervised test time training (TTT) loss, averaged across test sequences of length 2048, for the initial three TTT layers within a network comprising 125 million parameters. The figure demonstrates that a single step of gradient descent effectively lowers the TTT loss from WT-1 xt to WT xt. As the token index T progresses through the test sequence, the loss WT xt continues to improve relative to the initial loss W0 xt. To enhance visual clarity, the loss values are averaged over a sliding window spanning 10 time steps. For comprehensive results encompassing all 12 layers, refer to Figure 17 in the appendix. Figure 7 presents a high-level computation graph of the first TTT mini-batch, illustrating the relationships between variables and computations. The nodes in the graph represent variables, with blue nodes indicating input variables and yellow nodes indicating output variables. The edges between nodes represent the computations that link these variables. Notably, subsection 2.4 explains that G1, GB, which are not connected, can be computed in parallel as they do not have sequential dependencies on each other. This parallelization is crucial for efficiency. Additionally, subsection 2.5 mentions that the intermediate variables GS and WS, represented by white nodes, are not materialized in practice, allowing for the computation of output variables in a dual form, which optimizes the use of computational resources. Figure 8 presents ablations on the TTT mini-batch size B, where B equals 1 represents online gradient descent, GD, and B equals T represents batch GD. The left panel shows that smaller values of B improve perplexity because more gradient descent steps are taken. The perplexity of 11.09 at B equals 16 corresponds to the final result of TTT linear in Figure 11. The right panel illustrates the forward time in dual form with a context length T equals 2048. The total time, orange, is decomposed into the time for computing the WS at the end of every mini-batch, blue, and the time for Z1, ZT, orange minus blue. The time complexity for the WS is O, T times D2, which is constant in B, but the blue line decreases as larger B allows more parallelization until hardware utilization saturates. The time complexity for Z1, ZT is O, T times B times D, so the orange line initially decreases with more parallelization, then increases as the extra computation for Z1, ZT becomes dominant. Figure 9 illustrates how parametric learners define two key attributes, the model and the optimizer. On the left, these attributes are shown, and on the right, it is demonstrated how each learner uniquely induces a TTT layer. Specifically, the paper introduces two such layers, TTT linear and TTT MLP. Notably, the TTT layer with a linear model and batch gradient descent is equivalent to linear attention, a well-known RNN layer. Figure 10 illustrates the relationship between RNN layers and TTT layers within the broader context of sequence modeling layers. It highlights that RNN layers maintain a hidden state of fixed size across time steps. Similarly, TTT layers with parametric learners also have a fixed size hidden state, making them equivalent to RNN layers. On the other hand, TTT layers equipped with non-parametric learners can represent self-attention mechanisms, as detailed in subsection 2.6. This distinction underscores the versatility of TTT layers in capturing different types of sequence dependencies. Table 1 presents the ablation studies on improving from linear attention. All models in the table have 125 million parameters and are trained according to the recipe in subsection 3.1. The last row, with a perplexity of 11.09, represents the final result of TTT linear as shown in Figure 11. Beginning with the equivalence discussed in subsection 2.6, the introduction of learnable W0 slightly affects performance, but subsequent rows demonstrate that training stability is compromised without it. The most significant improvement is attributed to the transition from batch gradient descent, B equals T equals 2048, to mini-batch TTT, B equals 16. The second most impactful change is the instantiation of the inner model F with layer normalization, LN, and residual connections. These design choices are facilitated by the conceptual framework of TTT, which would otherwise be challenging to implement. The experiments were conducted using two primary datasets, the PILE for context lengths of 2K and 8K, and Books 3 for context lengths ranging from 1K to 32K. These datasets were chosen to evaluate both standard and long context capabilities. The backbone architectures for the models included both Transformer and Mamba, with TTT linear and TTT MLP models primarily using the Mamba backbone. An ablation study was also performed within the Transformer backbone. The evaluation protocols strictly followed those in the Mamba paper, using model sizes ranging from 125M to 1.3B parameters and training all models with the chinchilla recipe. Hybrid architectures were not experimented with to maintain clarity in academic evaluation. Figure 11 presents evaluations for context lengths of 2K and 8K on the PILE dataset. At 2K context, TTT linear demonstrates comparable performance to Mamba, with their lines mostly overlapping. TTT MLP, M, shows slightly worse performance under large flop budgets. At 8K context, TTT linear, M, and TTT MLP, M, significantly outperform Mamba. Even TTT MLP, T, with the Transformer backbone performs slightly better than Mamba around 1.3B parameters. This figure highlights that as context length increases, the advantage of TTT layers over Mamba widens. Additionally, Transformer maintains good perplexity at 8K context but is not competitive due to its high flop cost. Figure 12 presents evaluations for context lengths of 2K and 32K on the Books dataset. At 2K context, Mamba performs slightly better than TTT linear, which is a change from the observations made on the PILE at 2K context. However, at 32K context, both TTT linear and TTT MLP demonstrate superior performance compared to Mamba, a trend consistent with the findings from the PILE at 8K context. Notably, TTT MLP with the Transformer backbone also shows a slight improvement over Mamba at the 32K context length. These results suggest that as the context length increases, the advantage of TTT layers over Mamba becomes more pronounced. Figure 13 presents experiments on books with varying context lengths from 1K to 32K, treating context length as a hyperparameter. The figure connects selected points for transformers trained from scratch and fine-tuned, labeled as TF pre-train and TF fine-tune. Notably, TF fine-tune significantly outperforms TF pre-train, benefiting from long context without excessive training flops cost. The best performing methods, TTT linear and TTT MLP, show nearly overlapping lines. The left panel of Figure 2 provides a zoomed-in view of Figure 13, focusing on parameters between 350M and 1.3B, excluding TF pre-train for clarity. Figure 14 compares the performance of TTT MLP and TTT linear across different context lengths. It shows that TTT MLP performs slightly worse at short contexts, but significantly better at long contexts. This aligns with the expectation that MLPs, with their more expressive hidden states, are better suited for handling longer contexts. Both TTT linear and TTT MLP have matched training and inference flops, ensuring a fair comparison. The transformer baseline, with 2.8 times the inference flops, has an inherent advantage due to its higher computational capacity. Figure 15 presents a benchmark conducted on an NVIDIA A100 GPU equipped with 80G HBM and PCIe connections. The left panel replicates the data from Figure 3 but incorporates TTT-MLP. Notably, the transformer baseline exhibits significantly faster performance compared to the Mamba paper's findings, attributed to the utilization of the state-of-the-art VLLM serving system instead of the Hugging Face transformer. The right panel highlights that during the generate, decode, phase, TTT linear and Mamba demonstrate nearly identical latency, which is notably lower than that of both the transformer and TTT-MLP. In the related work section, we discuss several key areas of research that are relevant to our study. Firstly, we look at structured state space models, SSMs, where Mamba is positioned among other models like TTT linear and TTT-MLP. These models differ in their hidden state representations, with Mamba using a vector state, while TTT models use matrices, allowing them to compress more information in long contexts. Secondly, we delve into test time training, TTT, which involves formulating a learning problem for each test instance. This approach often uses self-supervised tasks and has shown significant improvements, especially in autoregressive settings. Lastly, we explore the concept of fast waits, which update parameters on the most relevant data. TTT can be seen as a special case of fast waits, with the key distinction being the formulation of an explicit learning problem for the test instance. In this discussion, we highlight the reformulation of the supervised learning problem as learning to learn at test time. This approach introduces a new conceptual framework for network architecture design, as summarized in Table 2. The search space for effective instantiations within this framework is vast, and our work represents just an initial step. Future research could explore alternative parameterizations for multiview reconstruction tasks, improvements in systems optimization, and the potential benefits of longer context and larger models. The motivation for studying test time training, TTT, stems from its closer alignment with human learning processes, which do not rely on ID instances or a train test split, but rather on long sequences with temporal dependencies. Thank you for watching.